All right, guys, good morning. We'll get started. So whoever could join us, but whoever who couldn't join us, they'll just have to join us offline later on. So next week we're coming back to school. So I just want to highlight a couple of things. You know, when we go through the lesson notes, and then in your lesson notes, there are something which have numbers on the side, like it's got 1.1.1, 1.1.2, or in the atomic structure topic, there will be 2.1.1 in the lesson objective. So just in case you don't know, you are on the bonding topic now. So the bonding topics start from 2.4 and 2.5, as well as 2.6 and 2.7. So there are 4 sections in there. So in the notes, you will have the learning objective as 2.4.1, 2.4.2, such as the one in the notes. You will see that this is for covalent bonding. So you've got 2.5.1, 2.5.2. So when I say Cambridge syllabus, when I say look at the syllabus, these are basically the numbers. You can either look straight from the master document, which I did print it out for you, or you can just look at your notes and you're supposed to have done a checklist of all these things which Cambridge say candidates should be able to do. Okay, so whatever is stated in the syllabus is the minimum you must know, because if there are anything in the syllabus that you miss out on, then you will have problem because Cambridge told you to know. For instance, this is covalent bonding. Each of these, I think I made sure that pretty much everyone knows how to draw for each of these, including counting the number of covalent bonds, because my strategy has always been to draw the display formula, count the correct number of covalent bonds, and then draw the dot and cross. That has always been my strategy. I outline it very clearly in the series of lecture tutorials as well as the work, and therefore you should hopefully be able to do what I expect you to be able to do. Okay, so I just like to very quickly go through the syllabus because so far you have gone through the lectures yourself. Okay, you don't become an expert by going through things once. So I thought it'd be quite nice for me to review the syllabus a little bit, okay? Of course, next week, topical test. Everything comes down to this 2.1, describing the differences between element component mixtures. So make sure you know definitions, how to spot in the diagram and stuff. And of course, all these are atomic structure. You started on this just before the SSRU exam, and you continue further just after the SSRU exam. So there was a bit of a disruption, but hopefully I have reviewed the topic enough that you know what each and every one of these mean. I've also returned your multiple choice atomic structure number 5. So back then I had the 1 and 0 correct and wrong, but I have annotated the script that you submitted, and I've returned the atomic structure work 5, the MCQs. People thought MCQs are easy, but it's usually the more difficult paper because it involves a lot of theory that you need to be able to argue with yourself and not make any mistake at all because there's only one correct answer. Things like noble gases, like helium. Helium, you know, doesn't have 8 electrons in the outer shell because it's only in the first shell, but it's fully filled out the shell. Things like group number. This is very important in the bonding topic as well. Group number tells you how many electrons you have in the outer shell, but it only tells you up to the group 7. According to the syllabus, it only tells you up to group 7 because when you have group 8 or noble gases, things like helium doesn't have 8 electrons in the outer shell. So be very careful. Period number, how many electron shells get occupied. Something is quite wrong with this thing, fluorine, chlorine, bromine, iodine. So we know that this is period number 2, 3, 4, and 5. In the syllabus, they say you should know up until element number 20 for electronic configuration. So you don't need to know electronic configuration for bromine and iodine, but there is a problem. When question asks you to draw dot and cross, some people try to get the electronic configuration of bromine and iodine. Nothing wrong with that, except that you are not doing it the right way. If you look at the atom, we will know the number of electrons equal to number of protons because it's an atom with no charge. So when you get the electronic configuration, I mark a cross there because you will see your number of electrons doesn't match the number of protons at all. Okay, so that is beyond the periods in the chemistry that you need to know in O level, but you get to do them in A level. You get to that level. Okay, but what is important is These are all group 7. So group should be GP. I'm not too sure. My handwriting is really terrible. So a lot of you have written down G in your annotated notes. So group 7 have 7 outer shell electrons because they're all in the same group. So what you have is fluorine, fluorine, chlorine, chlorine. They all form a single covalent bond because with 7 outer shell electrons and being bonded to itself non-metal, so they will just form a single covalent bond. When you convert this to dot and cross, do not forget to use a dot and cross to represent the differences, and do not forget to include all the other electrons because you have 7 outer shell electrons to begin with. Counting the dots and counting the crosses remains something difficult for a lot of students, so make sure you are able to do things like that. Okay, so what else? Isotopes. So some people are still confused within isotopes. So, you know, like in a multiple choice setting, or sometimes question will try and confuse you. So we know that isotopes have the same chemical properties. And the only reason for that is because it's to do with the electrons and the electronic configuration. So just because you are choosing something correct does not mean it is the correct reason. Just like in your bonding essay, the one on graphite and diamond, just because you are writing something which is correct from the notes does not mean that you are answering the question. So you need to be very careful. It is called context. Are you answering the question, or are you simply choosing information that you write without relating it to the question? So the first thing you must ask yourself really is this related to the question? You brainstorm very quickly in your head, and you can scribble some stuff on the side. Then when you write down your answer, your essay, you get straight to the point. No need full sentences because you're not doing an English exam, you're doing a science exam. Straight to the point, have your points of interest. The number of lines should indicate how much to write. If you have been writing too much, you might have just been wasting your time. So you need to really learn how to summarize your stuff. Things like graphite and diamond, which I'll mention a little bit, you really need to know how to prepare certain stuff for them. Some questions always come up again and again, so you should be able to prepare for them. Now, reading information like this, the 12 carbon and the 35 chlorine 35 like that, this number on top, I just want to highlight to people, this is nucleon number, this is not neutron number. I think Africa had a bit of a problem back then, not too sure about now. As for the definition of these things, you can go back to the previous syllabus. So the syllabus is a great document because you see proton number, atomic number, definition, mass number, or nuclear number, definition. The syllabus is provided for everyone. So everyone had the same opportunity. And I'm simply showing you that if you use this document fully, you don't just read it, you use it fully, you know that this is in the syllabus, you will be fine, okay? Counting protons, electrons, and neutrons, I think most people are okay now because we have used those concepts to continue further onto ions and ionic bond. Because if you don't understand the idea of metal losing electrons to give you the positive ions and non-metal losing, metal, let me just clarify myself. Metals on the left side of the periodic table, and then the non-metals on the right side of the periodic table. So to complete the outer shell, the metal will lose electrons. And then the non-metals, usually they can share electrons if their partner is non-metal. But if their partner is metal, there will be a transfer of electrons from the metal to the non-metal, and therefore they will form negative ions. How do they become negative ion? They must have gained the negatively charged electrons. And then when you have giant ionic lattice, if you look at this carefully, there are four different structures. Make sure you know that there are 4 different structures. The first one you learned is called giant ionic structure. Okay, so I just want to highlight a few things. So remember I told you to summarize and write down these 4 things, because these 4 structures, they are everything. Even when you go on to A levels and you go on to university, you come back to these 4 structures, okay? Structure must have giant or simple. So the first one you learned was giant ionic structure. You should be able to how it looks like. You should be able to sketch how it looks like, because that is your definition just now. it has an alternating cation and anion. So you don't have electrons because when you have ions, the electrons are not free at all. The electrons are inside the shell. So these are called localized. Localized means they are not free at all. The electrons are in the shell. If you label these are not electron. This is anion, and this is cation. And the way you describe it is you have alternating cation and anion. Actually, you have 3 dimensions. If you think about the structure of NaCl, what you have is the Na plus is surrounded front and back, left and right, top and bottom, something like that. So Cl minus is surrounded by Na plus, and then the Na plus is surrounded by Cl minus, and so on and so forth. So hopefully that makes sense to you. So it's a continuous structure. Okay, this is just in 2 dimensions, alternating cation and anion. We label our diagram. Now, the most important thing is physical property. This word is called physical. Physical because it has got nothing to do with chemical. So when they ask you on physical properties, they are not asking you on chemical properties. Something like acidic or alkaline or whatever, those are chemical property because it reacts with something else. Physical usually is to do with conduction of electricity, is to do with melting point and boiling point. So ionic compound has a high melting point and boiling point, okay? And the reason is because what do you need to break? So we specify the structure. So there's no such thing as giant ionic bond, okay? So some people, I think it was Nora, if I'm not mistaken, so she would put down things like giant ionic bond. There is no such thing as giant ionic bond. Be very careful when you specify giant or simple is to do with structure. So here, you need to break strong ionic bond. So this links well to your work as well. You will see the essays keep on coming up again and again. So this is break strong ionic bonds, and this is between oppositely charged ions. You need to be very careful about your choice of words because words are everything. When you use the wrong term, you will mess up the whole thing. I remember there were 1 or 2 people in this class who specified that diamond, you know diamond? So they said that diamond has a giant ionic structure, which is completely wrong. Because when you think about diamond, that one is just carbon bonded to 4 other carbon. So when you have diamond, you cannot have ionic structure because when you have ionic structure, you must have cation and anions. The cation comes from metal, usually. The anion comes from non-metal, but you can also have polyatomic, like ammonium ion, like sulfate ion, like nitrate ion. So it's not just metal and non-metal, but as long as you have positive ion and negative ions, you have ionic compound. Here, you have non-metal and non-metal. You don't have ions, you have atoms, and you have covalent bond. So covalent bonds and ionic bonds, they are different. So be very careful. You don't see any ions in here at all. So it is not even ionic to begin with. So before you write something, try to think about it first, okay? As a result of this giant ionic structure, you have a strong ionic bond. This nature is called electrostatic. Some people couldn't spell this properly. Electrostatic means something positive and something negative. Sometimes your negative is electrons, such as metallic bonds, but here in ionic bond is between oppositely charged ion. They specify this because you need to know what are the particles inside the structure. It's not electrons, it is positive and negative ion. Now, some people say ionic compound conduct electricity when molten because it has free electron. That is wrong because when you draw the cation and anion, when you draw the dot and cross, you don't show the electrons outside because the electron get transferred from the metal to the non-metal. So the electrons are not free at all outside. When you say free electrons, it doesn't make sense at all because you know there are no electrons that are not inside the shell to begin with. Okay. Now the next thing is describe. This word is very tricky because they say describe. So you need to know how to draw, and then you also need to know how to write in words. When you are writing in words, that is your actual last work. To be honest, the work 4, if I'm not mistaken, I'll show you in a little bit. This is between metallic and non-metallic elements. So they specify even though you could have things like ammonium chloride, but this is not metallic elements. So yes, you do have ionic bond here, but they won't ask you to think about the formation of the ion here. They will just ask you between metal and non-metal, including the use of dot and cross diagram. Dot and cross diagram, let me just show you in one of these work. I think it was work, not work for, doesn't matter which work it is. Let me just show you one. Where was it? I was going to say. All right, so I think this one is labeled as work 4 on yours. Okay. Now this is, I give you some time to actually find the work. So you should have already gotten the work next to you. Yeah. So for example, this is astatine. It reacts with magnesium to form magnesium astatite. As you know, astatine is below chlorine and bromine and iodine. So you have a group 7. So you have At minus and you have Mg2 plus. Your job really is to think about where do they come from. The Mg2 plus come from magnesium. The At minus come from At. Those are atoms. This is group 7. This is group 2. So when you're a group 2 metal, so this is the kind of question that was straight from the syllabus, right? Describe how it is formed. There are no diagram here. So it's not doing a diagram, it's using words, describe. So magnesium to magnesium 2 plus, the magnesium atom loses 2 valence electron or 2 electrons from its outer shell. Now, you have a problem here. The most common problem that people have is people talk about magnesium ion loses 2 electrons. That is wrong. This is a result of the atom having lost 2 electrons. So again, it comes down to the words, okay? Now, another common error is people say it loses 2 electrons. What is it? I specify first magnesium, so it refers to magnesium. But when you start the sentence with it, there are 2 things in here. Which one are you referring to? So sometimes just be very straightforward with the English, but be very specific. What are you talking about? Okay, just because you understand it does not mean other people have to understand you. So you need to make it very easy, very simple for them. The astatine atom has 7 valence electrons. So you just need to gain 1 more electron. So just need to gain 1 more electron. So some people thought you need 2 more electrons because they saw the formula. They saw the formula there. The formula there means you need 2 of these ions, but it does not mean you gain 2 electrons, because when you gain 2 electrons, you become 2 minus, but this is minus 1. That is because of your lowest common multiple. So when you have magnesium atom, you need 2 of the astatite because you have 2 electrons, 2 add 2, 1 of it goes there, and then the other one goes there, because here you already have 7, so you just need to gain 1 more. Here you already have 7, you just need to gain 1 more. Why do I need 2 of them? Because I have 2 electrons to give away. I need 2 of these in order to accept 1 electron each. When you draw the dot and cross, you will just have 7 of the dot and then 1 cross, or 7 of the cross and then 1 dot. Dot and cross, make sure you have the difference between the 2. I think it was Shaira who didn't really do the dot and cross properly. Okay. Ultimately, what is the objective? Why in the world do you lose 2? Why not 3? Why not 1? Why in the world did you just gain 1 electrons? Why not 2? Why not 3? Because both of them, they simply want to get to a fully filled outer shell, fully filled valence shell. That is the purpose of ionic bonding. That's the purpose of covalent bonding to begin with. Okay. Now the next bit is always the kind of questions associated with ionic compound. Doesn't matter what ionic compound they give you, as long as it's an ionic compound. You see, how do I know it's ionic compound? Mg2 plus, At minus, oppositely charged ion. So you will have high melting and boiling point. And I talk about conduction of electricity. These are as stated in the syllabus. If you go back to the syllabus, describe and explain. So describing, the question just now was asking you to state, right? So this is just describing, but not explaining. It does explaining what is the structure, giant ionic lattice structure, what needs to break, very strong ionic bond between the oppositely charged ion. So again, structure and what needs to break for melting and also for boiling. Focus on what you need to break rather than repeating the question, high melting and boiling point. Okay. The next thing is conductivity. When you are aqueous or molten, you have free ions. Free ions means ions are mobile. They are free to move. They can move freely. And then you cannot talk about free electrons. When you talk about these free electrons, it's entirely wrong. When you draw the dot and cross for this cation and anion, you don't see any electrons floating around. Remember when you do the crisscrossing just now, the Mg2 plus and At minus, so you have 2 and 1, which is the valency. So you're saying the electrons get totally transferred from the metal to the non-metal. So you're saying that the electrons are not floating around outside. All the electrons from the atom goes to the other atom, and then you get cations and anion respectively. So hopefully that makes sense to you. You do not have free electrons. You only have the ions. They are no longer held in a fixed position when you melt them or when you dissolve them in water. That's why you can conduct, but not when you're solid. Be very careful about that. Okay. The next thing is on covalent bonding. So a lot of people thought the definition of covalent bond is sharing of electron. That is number one mistake. Okay. So be careful. This is about the formation. This is not definition. This is formation. So what is covalent bond then? Covalent bonds, just like ionic bonds, it is to do with electrostatic force of attraction. So this word again, positive attract negative. So electrostatic force of attraction. The key here really is what is your positive and what is your negative. Okay, let's go to the second structure. So the second structure I'll be talking about are things like simple covalent bonding. By right, I usually like to talk about the three giant first, but it doesn't matter. Let's just move step by step. The fact that you have a simple structure, it has to be the covalent thing then, but simple covalent structure has a low melting and boiling point. The fact that you have a simple structure is associated with low melting and boiling point. Describe and explain the properties of simple molecular compound. Describe and explain. The moment you see low melting and boiling point, there is to do with simple covalent molecule. Poor electrical conductivity does not conduct when solid, does not conduct when liquid, aqueous or gas, does not conduct at all. Does not conduct at all. Okay, definitely covalent. Okay, so what do we have? What we have is a single, discrete. Discrete means individual. Discrete means individual molecule. So later on, you will learn something called molecular formula. So simple covalent structure has something called individual molecules. So you will be able to count the actual number of atoms in one single molecule. That is because what we are breaking is we are simply breaking the weak intermolecular. Inter means in between. So we are breaking the forces of attraction. And these forces of attraction is something positive attract something negative, such that if I have Br like that, but I also have other molecules of Br. So what you will have is you will have like that. So there's attraction between the molecule. This is one molecule. This is another molecule. This is another molecule. When you go from solid to liquid to gas, you're changing states of matter. Remember, not everything boils at 100 degrees Celsius because not everything is water. Okay, so this thing in between the molecule, this is between the molecules. That is what you call intermolecular forces. Whereas you have the covalent bond. Covalent bond is always strong. Okay, so some people in this class, you have mentioned about breaking weak covalent bond. It's ridiculous. You do not break weak covalent bond. Covalent bond is always much stronger. It is the intermolecular force that is weak there. Be careful. The reason why you cannot conduct electricity, because when you have simple covalent molecules, there simply isn't any free electrons because the electrons are all inside the shell. Here they are localized because they are fixated in between the two nuclei. The nuclei are positively charged protons. The localized electrons, they are forming the covalent bond. They are attracted to the two protons in the nuclei, to the two nuclei which contain protons, and therefore that is your ion. There's a covalent bond there. Okay. So these are all the structures that you're expected to be able to draw. Just want to highlight some of the difficult one. HH, well, actually not difficult, I guess, because I'm an expert already. Oxygen is in group 6. So that means when you're in group 6, you only need to share 2 more electrons with the non-metal, and therefore oxygen will form 2 covalent bonds. This is 1, this is 2. Things like CH form, carbon is in group 4. So carbon always form 4 covalent bonds because group 4 means 4 valence electron. Group 4 means 4 valence electron because the number of outer shell electron is equal to the group number. You did topic 2 before this topic because everything is related. Now NH3, when you have group 5, you have 5 outer shell electrons. Then you just need to share 3 more electrons because when you have 5 electrons, share 3 more, then you will have fully filled outer shell. When you draw the dot and cross, do not forget single line means 1 dot, 1 cross usually, okay? And then you have CH3OH. These are slightly more tricky, but they are not impossible. So carbon form 4 bond, hydrogen form a single covalent bond, oxygen can be double bond, like oxygen, oxygen, double bond like that. But oxygen essentially form 2 covalent bonds, 1 and 2, 1 and 2, because group 6, they just want to share 2 electrons to complete the outer shell. C2H4 is the most difficult one that people couldn't draw properly. I think it was work 3, wasn't it? Yep, so this is example of C2H4, and this is example of PH3. So phosphorus is just below nitrogen. This is the kind of question where they might not ask you NH3 straight away, but they will ask you something similar. Okay, they can ask you to draw NCl3 as well. They can ask you to draw PBr3 as well, because all of them are related. So when nitrogen bonded to chlorine, the chlorine is in group 7, the bromine is in group 7, so they just need to form 1 covalent bond. Group 7, you have 7 valence electron. That is the meaning of group 7. So I can count the nitrogen, group 5, and then share 1 electron, 6, share another electron, 7, share another electron, become 8. The chlorine, group 7, share 1 electron, become 8. When I draw my display formula, this is correct. When I draw my dot and cross, how do I translate that? Because they want dot and cross. I know this is not what the question is asking, but I'm showing you what you could do. Very, very powerful method, okay? I don't like to draw shell because for me, they are a bit cumbersome. As long as I show this being a 1 dot and 1 cross, so single covalent bond, 1 dot and 1 cross, single covalent bond, 1 dot and 1 cross, single covalent bond. Do not forget your nitrogen is in group 5, so you use 3. If I say cross is nitrogen, I use 3 out of 5. So I still have 2 more. Now I count my cross, 1, 2, 3, 4, 5, original from nitrogen, and then share 3 more from the chlorine. Now I have to worry, is this hydrogen or is this chlorine? I'll tell you something funny. I think Rahiman was the one who did this mistake. He drew the hydrogen with 7 outer shell electrons. Yes, it will happen, not only to Rahiman, but it will happen to some of you if you do not understand the first 20 elements, because as I did mention, knowing the first 20 elements is very important. It gives you that extra edge, okay? So to be a competent chemist, you need to know the first 20 elements, so you know their positions. The more you use it, the better you are with vocabulary and stuff. So I could ask you PCl3, I just need to change the nitrogen to phosphorus, draw the outer shell only. I can ask you PBr3, I just need to change that to Br, and then I could get PBr3, showing the outer shell electrons only. So hopefully it makes sense to you how you can use this kind of display formula, count the covalent bond correctly, translate it to dot and cross correctly, make sure whatever you do, count the outer shell electrons. I've just done that in an instant without drawing the shell. For me, shells take a lot of time because people want to be neat and stuff. In the end, they are wasting more than enough time on that 2 marks question. All right, so the next one is about eating. So some people, I'll show you what I mean, yeah, okay? So some people, they just draw something like this. So they saw CH2, CH2, right? Or C2H4. The carbon here formed 3 bonds. It's not happy. There is 1 electron there and 1 electron there. So what it does is the carbon really want to form 4 bonds, except for graphite. Graphite is a special case. We'll talk about it in a little bit. So here you have double bond, 1, 2, 3, 4 around this carbon. Now look at this carbon, 1, 2, 3, and 4. That one is happy. when you go to this acetylene, so you don't really do this in the syllabus because it wasn't stated, but to give you some information. Triple chocolate mean 3 times chocolate. Triple covalent mean 3 times covalent. But then I also have hydrogen atoms because they don't mention us what happened at the end there. So when you have triple bond there, 1, 2, 3, the carbon can form one other covalent bond. So this is how I represent sharing electron. Some of you have done things like this. That is not really acceptable to draw it like that. Your purpose is to show it sharing. I know what you want to do, but it's getting to an extent where it's quite messy. So you need to try and show your sharing like by showing them next to each other like that. Okay. It's just a preference. It's like nothing super wrong about it, but just want to highlight to you some standards. Okay. So these are properties of covalent compounds. So sometimes they might not ask you straight away, but they will give you in a table format. So you need to know how to read table. Now this is low. I can tell you some values like water. Water is a simple covalent molecule. Water boils at 100. So it's 100 high, it's 100 low. So low or high, it comes down to experience. You need to relate it, not just looking at that and say it's low, it's high. No, you also need to relate to other properties as well. Usually there are other information that will help you to decide. Decision is a very important thing to do for Cambridge exam. And to be able to decide, you must know some stuff. You must know about the structure and what exactly you are breaking. You see, weak intermolecular forces there. The conductivity is to do with no free electrons. Do not talk about ions because you don't see any ions at all. You see covalent molecules. So we talk about no free electrons in here. You don't see any free electrons in here. You talk about free ions versus no free ion when you have giant ionic structure. So 2 structures down, we still have 2 more structures to go. The next one is called giant covalent structure. Giant covalent structure is also known as giant molecular structure. You will see that the syllabus have used giant covalent structure. So you can expect the exam question will give you something like giant covalent structure. But I came from old school, which actually use giant molecular structure. So both terms are totally acceptable. You can use them interchangeably, but whatever you do not do this, yeah? So some of you did this. Just want to highlight to you, there's no such thing, yeah? Giant covalent bond, there is no such thing. You can have covalent bonds. Covalent bond can be strong, it's not weak, but you cannot have giant covalent bond, that is wrong. Giant or simple is to describe structure. Now there are 3 case studies, graphite, diamond, and silicon 4 oxide. Don't worry too much about the number here. This is also known as silicon dioxide. So these 3 structures, you need to know each and everything about it because describe, they come under giant covalent structure. The first thing that comes to your mind is giant molecular or giant covalent structure. I already mentioned graphite and diamond briefly. I'll talk more about SiO2. There is the relationship between structure and bonding. So you use graphite as a lubricant because you just need to overcome the weak van der Waals between the layer. They mention as an electrode here. That's because graphite can conduct electricity. I remember I haven't asked you anything in the work on this, but I also remember that in the notes, there was a mention of why graphite can conduct electricity. Because when you look at graphite, you are just using each. I forgot. I can just copy paste that. You're just using 3 out of 4 electrons. If you look at this carbon there, of course it's continuous, left, right, like that. So this carbon is only bonded to 1, 2, and 3 other carbon. You say the coordination number around each carbon is basically 3. What does this mean? Each carbon only uses 3 out of 4 valence electrons for covalent bonding. Having done that, you should see that there is 1 free electron. 1 free electrons per carbon. Now this electron is free. We don't talk about ions, we talk about electrons, and they can conduct electricity. Graphite electrodes is used in your battery. So when you have energizer or everyday batteries, any kind of AAA or AA, in between the sharp end and the flat end, If you peel the battery inside, you will see graphite electrode. We'll come back to this again and again in future topics. So make sure you know why graphite can conduct electricity in terms of the structure, in terms of the bonding here. This is usually 2 marks question. So be very careful. Stated in the syllabus, structure. So the structure there doesn't just mean giant covalent structure. It actually means what actually can you see inside the structure. Okay. Now, why is it as a lubricant? Because when you lubricate, you are sliding over the layers. So the layers can slide over each other easily. So why they can slide over each other easily? Because they just need to break, or they just need to overcome. Now, this is very important. Most of you just say weak intermolecular forces, which is not wrong. You do get the marks. So just be very careful. This is a specific thing. Overcoming the weak van der Waals forces. So you have the weak van der Waals. Make sure you spell the guy's name properly. These are covalent bonds. These are strong. These are van der Waals. These are what you need to break when the layers slide over each other. They don't talk about the melting and boiling point, but here it is related to their structure. What is the similarity in properties? So both of them is what you call giant covalent structure. So if both diamonds and silicon dioxide and graphite is giant covalent structure, what do you need to break? Well, when you melt or when you boil, you need to break. I don't know why I write down there. I should have written down. Down here. So structure. So we're just coming to an end, to be honest. Okay. So just bear with me. And today we're really just summarizing what you have learned for the past 3 to 4 weeks, okay? Giant covalent or giant molecular structure. You have a couple of case studies, like this is diamond. Make sure that in diamonds, your carbon forms 4 bonds. So what I'm doing here is I'm showing the branching. I'm showing the branchings just to sketch it out. And I'm just going to show very quickly the graphite. So I just want to copy paste my diagram so that I can save some time. So on the left-hand side, this one is diamond. This one is graphite. And then I also have one more, which is silicon dioxide. So silicon dioxide looks a bit more like diamond than graphite. So make sure you know how to sketch silicon dioxide as well. Silicon, just below carbon, they form 4 covalent bonds. So here they form single covalent bond times 4. And then oxygen, group 6, they form 2 covalent bonds. You need to be able to talk to yourself and be able to sketch this out. Oxygen form 2 covalent bonds, 1 and 2. So that is bonded to silicon. And then each silicon, it forms 4 covalent bonds. So I already showed 1. So I usually just extend it like that to show that it's continuous. So that is called silicon 4 oxide, or what I call silicon dioxide. Silicon 4 oxide is just the official name there. So all of these structures, you can see that this one does not conduct at all, whether it's solid or liquid or gas, but this one can conduct, very special. You use it as an electrode because it has 1 free electrons per carbon that can, flow along the layers, and therefore it can conduct electricity. Diamonds versus graphite. Now these are very, very important one. Diamond is hard, graphite is soft. Diamond cannot conduct, so it cannot conduct at all. But this one can conduct electricity, and then it can conduct heat as well. What other thing you can say? This one is very hard because if you go back to the work, I think it was this work, work 3. Diamond, graphite, yep. So diamond and graphite, there are 2 very common questions, yeah, okay. So talking about lubricants, some people just stop at talking about the giant covalent structure. But remember when we talk about structure, yes, giant covalent structure is the big picture. But when you look at the structure here, it's about the layers that allow it to act as a lubricant. So talk about the layered structure. And then talk about the weak van der Waals forces. When the layers slide over each other, you're just breaking these weak van der Waals forces. You don't change the covalent bond at all. But then when you want to talk about soft and hard, the soft nature is to do with the sliding of the layers. So you just need to break the weak van der Waals forces between the layers. I know in the notes, it's quite long, but then you need to try and understand for 2 marks, you need to write 2 points. When you write so long for graphite or so long for diamond, you don't have much more time or much more space to write for the other one. So you need to try and prepare the essay in a good way. You remember the key point. What about the structure? Not just about giant covalent, yeah? Because both of them have giant covalent structure. So you need to look specifically at how the structure is different. So when you want to change the shape, because hard or soft, hard means when you apply force to it, you need to actually break the covalent bonds when you want to change the shape of diamond. And to break covalent bond, that is strong covalent bond. Whereas to change the shape of these, they just slide over each other, and you're just breaking the weak intermolecular forces, the weak van der Waals forces. When we say intermolecular forces, usually we associate with simple molecule, but graphite is one extremely special case study that you need to keep your eye out for. It has a giant covalent structure, but it has got these weak van der Waals between the layer, and this layer structure makes it very, very special there. Describing two differences in the structure. Now, this is one thing where people don't understand, okay? This is not properties. You cannot talk about hard and soft. You cannot talk about conducting versus non-conducting. Structure, look at the structure. The carbon that is bonded to 3 other carbon, the carbon that is bonded to 4 other carbon. Difference number 1, okay? Similarity, what is similarity? They have covalent bond. They have covalent bonds between the carbon-carbon atom. But they want differences. So what is the other difference? What else? This one has van der Waals forces between the layers. This one doesn't have van der Waals forces between the layers. I mean, go for the simple one, okay? Go for the simple one. Some people talk about the layered hexagons, the layered structure versus non-layered structure, 3-dimensional rigid tetrahedral framework, slightly more complicated, but that is acceptable as well, okay? So when you're an examiner, you are marking thousands, maybe 10,000 papers. Your job is very difficult if the student make it difficult for you. Your job is easy when you just read and you can understand what the student wants to say. Student gets straight to the point, okay? The use of diamond. Okay, some people put down jewelry. So jewelry, you know, like ornament and stuff. I don't know, did I spell that correctly? Jewelry. Okay, that is wrong because it depends on the hardness. You go for jewelry because of its shiny nature. That's what makes it expensive. Okay, but yeah, you actually use it for making those drilling ends, you know, like the bit where you want to go into the concrete or mining into hard ground. That's what diamond is used for. Yeah, I think that work is fully okay. I think just some notes on this. I already mentioned the electronic configuration. Please don't try and work out the electronic configuration. All that is needed is group 7 outer shell electrons. That's it. Okay. I think most people are okay with that. Okay with that. And this one. Let me just go straight to the first question. Yeah. So I'm just going to go through the work now. So in terms of boiling point, this alone tells you that this is most likely simple covalent. But then we can also think about the conductivity when molten. This can conduct. If you are a compound, you are not graphite. Bromine reacts with something else. So these are not graphite, cannot be graphite. So they have high melting and boiling point. So it's giant structure. It's not graphite because it's a compound. Okay, graphite is an element. Graphite contains only carbon atoms. Now, when molten, they conduct. So that means you are not covalent. You must be ionic. Because if you're a covalent compound, you cannot conduct at all. So which one is bonded covalently? Looking at the boiling point, it does not tell you at all because you can have giant covalent structure which have high melting and boiling point. You can have simple covalent structure which has low melting and boiling point. So it really comes down to choosing the right reason for that. And for that 1 mark, you might get penalized if you don't choose the correct reason. This is silicon dioxide. This one, you don't really learn it, but they already told you low melting point. Low melting point. So talk about the structure. I think Shaira didn't do very well in this explanation if she's still around. So talk about the structure for each one. For each one. Afika also, I think she stopped at talking about silicon dioxide, but she did not talk about polyethylene. If I'm not mistaken, there's Afika. Okay. Now structure. What do you need to break? The strong covalent bond. Many strong covalent bond. Okay. Do not talk about ions when you talk about covalent bond. Now, the polyethylene, simple covalent structure. You can use simple covalent structure, nothing wrong with that. You can use simple covalent structure, is perfectly fine. And then Just choose either one, no need to use both. Yeah. Then you need to compare what you are breaking. The weak intermolecular forces attraction doesn't require as much energy. Please do not try and repeat the question and say, oh, the melting point is 1610. Therefore, polyethylene also start to melt at 130 degrees Celsius. Repeating question is a waste of time and you are annoying. You are very annoying the examiner if you try to repeat the question. It's like the examiner will be thinking, oh, what is the student trying to do? Just wasting time in the exam. Straight to the point, structure, what do you need to break in terms of the energy required? Okay, so this work is done. Let me just go back to the syllabus. So that was it on that. So when you want to melt, melting or boiling giant covalent structure, you need to break many strong covalent bond. Okay, the strong is the adjective. Remember, covalent bond cannot be weak. Covalent bond is always strong. Now, the very last structure is to do with metals. Metals, you will see, metallic bonding need to be described. This is definition. Again, this word, positive attracts negative, is called electrostatic, but your negative is no longer negative ions. It is delocalized electron. Delocalized means they are not inside the shell. Why are they not inside the shell? Because there is no non-metal. There is nothing to accept the electron. The electron is just being lost from the outer shell of the metal atoms. Then you get positive ions and you get delocalized electrons. And of course, we know metals can conduct electricity very well because you have free electrons. Because these are not localized electrons, these are free electrons. We say free electrons, not free ion. Why? Because the ions do not move. The cation is stationary. They do not move at all. When you turn on a current and the bulb lights up, it's to do with the electrons flowing in the electrical circuit. It's got nothing to do with the cation moving. Malleable and ductile. So some areas in Qidang, I believe, is still using copper wire. Copper wire for the internet connections, because copper can be made into very fine wire. So you can make, or you can draw into very fine wire. So like electrical cable relies on the ductility of metals. Every single metals are elements. Be very careful, yeah? Every single metals are elements. When you look at periodic table, the middle block, so there's group 1 and group 2, and then group 3 to group 8, the middle block of the periodic table, those are all called transition metals. Transition metals are elements. All the metals are elements. Metallic bonding does not exist in compound. Okay, now malleable. Malleable is the adjective. The noun is called malleability. So you can hammer, you can change the shape. You can hammer into thin sheets. So basically you can change the shape. That is very, very important. And you can mold metal into whatever shape you want. Okay, and I already talked about that. So let's just quickly draw the structure. How does metal look like? When you have giant metallic structure, so make sure you can spell the adjective correctly, yeah? Metallic structure like that. And then you need to be able to draw the diagram. I think Rahiman had a problem with drawing this diagram because I think his cation was of different sizes. Make sure you draw similar sizes and make sure your electrons are suspended somewhere in between. Do not move your electrons much closer to one end. They are delocalized electrons. A lot of textbook, they forgot to actually label this correctly. It is just the outer shell electrons that get delocalized because your metal cations want to have a fully filled outer shell by delocalizing the valence electrons. So you have high melting and boiling point. Why? Well, first of all, you have giant structure. So the high melting and boiling point is to do with need to break. You need to break, so melting or boiling, you need to break strong metallic bonds. So metallic is double L, yeah? And this metallic bond is between, now this is the one where you need to be very careful, okay? Between your metal cations, positively charged ions, and your sea of delocalized valence electrons. So your electrons are negatively charged. These are not ions because metals are elements. Element only contain one type of atoms. Okay. Now, because these electrons don't have shell, so essentially in the solid state, you would have essentially that actually looks like this. So it looks like the positive ions are touching each other. That's because in the solid state, the particles are tightly packed together. And then these electrons are simply hovering outside like that. So in the solid state, they look like that. But the electrons can move because the electrons are not in the shell. The electrons can move. And that is why metals can conduct even in the solid state. But then in terms of the malleability, so you have layered structure. I have purposely drawn it like tightly packed. So you have layers, or you can have layered structure. So kind of like graphite, but of course we don't have intermolecular forces. We have a three-dimensional structure because it's giant structure. So left, right, top, bottom, front, and back, three-dimensional like that. And then what happened is the layers can slide. The layers of what can slide? The layers of cations can slide when force is applied because you have the ions of the same sizes. Now this thing comes up in the topic of metal again. You see these are metals of the same sizes. Now I'm going to change this scenario now, which is why I said Rahiman's idea of drawing different sizes are not very good, because if I have big, if I have small, if I have big and then big, and then some small one, and then big and big. So what is happening now is I have different metals. So I still have metallic bonds because electrons are electrons. So whether you are electrons coming from one atom versus the electron coming from the other atom, they are all just electrons. So you can still conduct. Can conduct, yes. Can slide over each other? No, because they are different sizes now. So different size cation. So you cannot slide over each other anymore because you have different size cation. This thing is actually what you call mixture. Why is it not a compound? Well, first of all, metal and metal don't form a compound exactly. Mixture of metal is what you call alloy. And you know, mixture doesn't have to be a correct proportion. It doesn't have to be fixed proportions. Definition of compound is you must combine them in a fixed ratio. But mixture can be any amount, just a little bit of something else. Then you have different size cation. Then you have different sizes which cannot slide over each other, and therefore they are no longer malleable. So this one says not malleable anymore. Not malleable, not ductile anymore. And then that's it really for that structure and bonding topic. So there was just a review of the whole topic already. So I won't go through the whole thing, which we have done for the last 2 or 3 weeks. Now going through the work, I think most people are okay with ionic bonds. Are there any questions in this ionic bond work? Well, I can tell you something. Some students, a lot of people make some mistake. This is ionic bond. I think it's not level work 1 in yours. It's probably level work 2 or something. Doesn't matter. By the end of the topic, you have done all the work anyway. This was very badly done because people talk about molecules. Remember the particles just now? If you go back to the definitions in the syllabus, it says ionic compound is between the ions. So it's got nothing to do with molecules. This is for simple molecular. Properties, and properties. Melting point and boiling point, conductivity, potassium iodide, group 1, group 7. So this goes back to the syllabus, which I just want to highlight to you, the syllabus is extremely important. I'll share this PDF with you later on, but you already have the document, the small piece of booklet which I printed for you. That is the syllabus. Okay, you also have it in the notes as well. So properties of ionic compound. Ionic compounds have high melting and boiling point, good conductivity or can conduct when aqueous or molten, cannot conduct when solid. I can tell you every single thing in the Cambridge syllabus. The questions come from the Cambridge syllabus itself. So this is drawing the ion itself. So remember earlier, describe the formation of the ions. Okay, that is using words. If they want to describe the formation of the ion, showing dot and cross, then you have to show the sodium atom becoming this, losing 1 electron. The chlorine atom gaining 1 electron to form the ion. Dot and cross, they don't say draw out the shell, so you draw everything. Most of the time, the question will say draw out the shell, but read the questions and follow the question. And do not forget charges. When you lose the outer shell electrons, this one only now has 2 outer shell, 1, 2, and 3, period 3. When you lose the outer shell electrons, this is now your outer shell with 8 electrons. Okay, this kind of question comes up again and again. I don't want to talk too much into it anymore. They're pretty much similar to what we have done in the lecture tutorial questions. I purposely chose to go through those questions as part of the notes so that you have an idea of what to do when you come to real questions like these, okay? It's not just to be memorized. It comes down to whether you can describe the idea using your own words, structure, and what you need to break. Correct adjective, please, and the correct chemistry as well. And of course, the strength of ionic bonds depends on whether you have bigger charges or smaller size cations, smaller size anions, but usually you just look at bigger charge cation, bigger charge anion, there will be stronger ionic bonds, more energy is required, higher melting point. Counting protons and neutrons and electrons, I don't have to remind you, but I can tell you that these are all in the atomic structure test. So if you pick up the home learning pack, there was in anticipation of school not opening next week, but school is opening next week. So try not to look into the question paper as well. Only look at them when you're ready to do the test, yeah? So just be honest to yourself. And properties again, so these two are properties, so make sure you answer the question properly. Remember I mentioned ionic compound has got nothing to do with free electrons. The moment you mention free electrons, you don't get the marks because when you see the dot and cross, you account for all the electrons. The 1 electron from 1 sodium goes there, the other sodium goes there. So you know, there are no free electrons at all. The electrons are all in the shell. You're not talking about metals, you're talking about ionic compounds. Be very careful. Dot and cross. You can use cross here, dot here. Then you have crosses and you have 2 dots. Just make sure you use something different. I remember last time you only did up until here. So now that you've finished the whole topic, it's time for you to actually go back to this question and think about it from a fresh perspective. Just very quickly, these are metal, these are simple covalent molecule, this is a giant ionic structure. So you have 3 different structures as well as bonding. Very, very interesting question, like formations of ionic compounds from the metal and non-metal, where you need to break the metallic bond, where you need to break the covalent bonds, because you need to react them together and you get the transfer of electrons, describing it. These are the kind of essay questions you can expect in terms of section B. Section B type of question at all level is a longer type of question where you need to know how to structure your essay. Like when you write composition, you don't just write whatever comes to your mind. You have a plan, okay? So in terms of electrons, how the reaction describe the ionic bonding formation, ionic compound formation. So you got to talk about transfer of electrons. You got to talk about the sodium ions is formed by sodium atom losing 1 electron, fully fill out the shell. Iodine, group 7 valence electron. Don't talk about the electronic configuration, just talk about the 7 valence electrons, gaining 1 electron to get to completely fill out the shell for the iodide. I think that was okay. Work 2. If you go to this second work, I think in general, this was quite well done, but plural. So some people couldn't read the questions on plural. So not solid. This is called using the melting and boiling point. I just want to highlight, okay, you don't necessarily have to use this, okay? So I'm doing this here. This is temperature in degrees Celsius. If I have boiling point and I have melting point. So if I have melting point, before I reach the melting point, I haven't melted. You see, I haven't melted. This is what you need to tell yourself. Before I reach the melting point, I am still a solid because I haven't melted. After the boiling point, I am a gas already boiled because I already overcome the energy required. So whatever in between the melting point and boiling point, that is your liquid. That is something that should come to your mind. Okay, you have calculator, you are allowed to use calculator. So, work out whichever one. At 25 degrees Celsius, it hasn't melted yet. So hasn't melted at 25 degrees Celsius, definitely, already melted because not solid, already melted. So already melted, at 25 degrees Celsius. So methane and bromine already melted there. But the fact that it's plural, substances and are, so that means if you write only one, you haven't really checked through the whole thing. So hopefully that makes sense then. The liquid, so you need to find the difference between melting and boiling point and work out which one has the largest difference. These are 1 mark and 1 mark. You press a calculator very quickly. Some people talk about one thing, but they don't forget about the other thing. You see, they don't talk about bonding, right? And that's why people just talk about structure. They just say methane has simple molecular structure, silicon dioxide has giant covalent structure or giant molecular structure. They stop there. You just get 1 mark. The different melting point is to do with what needs to break. Yes, I know the question doesn't say bonding, but they're always together, you see? Just because you have the structure, but you don't talk about what breaks, you are not explaining the melting point. Be very careful there. I think dot and cross is usually okay. Dot and cross is usually okay. So just make sure you draw the dot there from the metal or the cross from the metal. And this thing was quite badly done. So you need to relate the group number. This comes back to atomic structure. The group number tells you the number of valence electrons, outer shell electrons, and you need to talk about the metals tend to lose electrons to form positive ions, cations. The non-metals tend to gain electrons when their partner is metal. In order to get both of them will become fully filled outer shell. That's the purpose, that's the objective, that's something you need to highlight as well. This goes straight back to topic 1. Some people are very bad with this. Arrangement is to do with order or regular. Okay, arrangement is not separation. Separation is to do with packing. Tightly packed, closely packed with a little bit of space. That is packing, that is separation. Okay, I go back to the syllabus because, you know, it's important to show you where in the syllabus. You see, in terms of particle separation, so this is tightly packed. So some people couldn't spell this properly. Yeah, T-I-G-H-T-L-Y. Okay, versus closely packed, but you have space in between with little spacing. That one is liquid, whereas gas are very far apart. Arrangement is to do with order or regular. That is solid. That is definitely solid. Okay. Motion is to do with vibrations about a fixed point. That is for solid, and liquid particles can slide over each other and so on and so forth. So hopefully that makes sense to you. Most people could do this as part of the 20 example I did ask you to do. They could ask you random stuff like FBr, Fi, I don't know, ClBr, etc., etc. Group 7 and group 7, just like chlorine, just like bromine, just like iodine, single covalent bond. 7 share 1, become 8. Become fully filled out the shell. I think most people are okay with these. These are very common questions, carbon dioxide versus diamond. The other one which is very common will be CO2 versus SiO2. So giant covalent structure and then simple covalent structure, similar kind of idea for this question, to be honest. Okay, structure and what do you need to break. Okay, structure, what do you need to break, structure, what do you need to break, and compare the energy required. The similarities between the bonds. Now, people don't understand this question, yeah? So what is the same? Covalent, covalent. The carbon form 4 covalent bond. The carbon form 4 covalent bond. You see, some questions are trying to be easy, but people are trying to be difficult. So, you know, read the question and try to understand the question. Similarities is plural, and there are 2 marks, and there are 4 lines. You need 2 points for that 2 marks. It comes down to exam skills there. And I think I already did that work 3. I already done that. And work 4. This is your next work. So yeah, that's it really, guys. That's it really for today. So I'm done talking, and hopefully that makes sense to you. And yep, I'll share the recording eventually, and I'll share the PDF with you soon after this. So, you know, just annotate whatever else you need. Instead of just printing it out, just try to write down the 4 structures, sketch them out, and what you need to break in order to melt or boil them. Think about properties, go through the syllabus. So Thursday is your topical test on atomic structure, and then next will be a topical test on chemical structure and bonding. There should be 1 work on metallic bonding due tomorrow. So metallic bonding is the easiest out of all the bonding because it's the simplest one. Doesn't mean it's the easiest, just Just that you need to know all the bonding, structure and bonding, extremely important. Okay, thank you everyone. Sorry for the long lesson, but it was required to review the whole topic, which you had done for 3 weeks, and that was done in just 1 hour. Okay, thank you everyone.
Thank you, sir.